forgot how to use.
Oh yeah, you're allowed to. They tell you.
All right, let's talk about to open the unit. We'll have series. This unit I know is like we should give a word of disclaimer too. Certainly people like have this like fear associated with series, but actually I would like you to associate like beauty, elegance, and things like that with it. And it's really not as bad as people say it is. I think people kind of psych themselves out for it. It is like mind warping to think about infinity in general, but we've been thinking about infinity all year, so it's like maybe not a big deal anymore. But yeah, infinity, whatever. Okay, we're gonna start with improper integrals. We're not gonna like do any series yet today, so you'll get that soon though, very soon. And these are tied together in an important and intimate way. So we have a couple different types of improper integrals. I was given this by Ms. Getz. I've modified the PowerPoint, so I hope the examples are still the same. We'll see. All right, so let's start by evaluating the following integrals with your calculator if you like. This is a good way to do it. Just use f in it. Notice they're all the same, just with one small change. In fact, you can do one, your neighbor can do the other one, whatever. And I'd like you to make some kind of conclusion based on observations you make. Yeah, is it blue? Well, which one? There's two items. Is it this one? Okay, put your name on it. Put your name on it. Here. You have your choice. What do you want? Okay. Red is important. It's a big moment in your life. Tell your neighbor what you're discovering. Too. Is that the whole?
Yeah.
Okay, you're also required to put your name on it.
Oh, I am?
Yep. Because you're going to lose it. I'm worried about you. Look at the variety of options I have here. Black might be a good choice. If you want a thinner black. That one's a little sharper. You put your first name and on your team yourself. What are you discovering, friends? It does seem, even with 10, and feel free, by the way, to put like 100 instead of 10 in there, it does seem like these integrals are getting closer and closer, and that it might even be meaningful to put what symbol here? Yeah, maybe infinity. And maybe you already have a conjecture as to like what the value of this integral will be if you take the infinite case. So our take today will be to use a tool we already have in our tool belt, and that's limits, right? So let's just integrate in general 0 to m or something. What would the? Let's do that symbolically. We can do this antiderivative in our own way here. Well, I guess I'm using a here. Right? This, you might be like, well, that's an ill-defined thing to have an infinity at the top as a limit of integration. I can't like put an infinity there. And in some ways, you're right if you have that criticism. So let's just do it for a finite value a, and figure out what that is. And for any given a value, here's the integral you get. For any given a value, this is the integral you get, -2 e to the negative a over 2. But there's no reason that we can't take the limit of this expression as a goes to infinity also. And that really is what we mean by this symbol. It's the exact same trick we use for infinite series too later. Like how can we even put an infinity on the top of a sum? And the answer is the same. Well, we interpret that to mean the limit as n goes to infinity of the sum from like whatever, k equals 0 to n. We do the same kind of trick. Is that what you were getting, by the way? Is stuff that was increasingly close to 2? Good. Is that the first one on there? Yeah. So yeah, you just you calculated with me just now your first improper integral by hand. There it is, right? You see how that's done? think Josh, you just said this a minute ago. We'll use these two words to describe integrals. This is, in some ways, startling that this should ever happen. It's not going to be true. I think you can imagine, because, I don't know, do you have a sense for what this, for example, what this graph looks like? Right? So like this nice exponential decay function. It's not obvious to me yet which functions have integrals that do and which functions do have integrals that do not converge. I think you can give, can you give me an example of a function on the again, on the interval maybe 0 to infinity that diverges, for sure, you think? Y equals x, right? Like, it's easy to think of some that maybe diverge. But like, I'm not so sure about, like, is it sufficient enough to just be like, well, it kind of goes downhill. So maybe if it approaches 0, is like that enough? Or is there like, so this is a good question to have like in the back of your mind right now. But it's okay, I mean, we can use calculus to figure out the answer on each individual case. So, but be looking for the larger conversation too. Okay, so let's try this guy here as well. Is this the next one? I don't know. Good. Success. Really, it's meant to be a little bit of the same process. The integral will be some work here. And just like the warm-up, we're going to like try to push you again a little bit on your integration techniques here. Can we do this? Because you need the symbolic integral to do this, to take the limit. So it might be a little bit of a trick to do the integration here. But then we're just going to apply the same trick. So we'll take the limit as, what's your favorite letter?
B.
What? B?
B.
B. Okay, so B goes to, this time, negative infinity of the integral from b to 2 of 2 over x squared plus 4. And you're like, yay, I'm doing so well. I understand improper integrals. And then you're like, oh, wait, but I forgot like my normal calculus. How do I do that integral? How do you do that? Do you have an antiderivative for that? What would you like to see here instead of a, I mean, do you have even an inclination? What does this even begin to look like? Is this, it does feel like inverse tangent, except wouldn't you wish that this was what? 1, right? So if you want something in life, have we said this before? Make it happen, right? So I think I can make that a 1. I'll just divide everything on the bottom. I'll like pull out that 4. Is that okay? From b to 2 of 4 times x squared over 4 plus 1. We're getting warm. Annoying to have to rate the limit over and over again, isn't it? But it's good for you. Okay. So yeah, I don't know. Do you want to just put like a 1/2? You can even pull the 1/2 outside the integral. You can even pull the 1/2 all the way out. So the outside the limit if you like. Pull whatever. So, but maybe we want it there. I don't know. Is that a good way to write it? Now we do have something that looks a little more like the derivative of inverse tangent. So then can you just do the u substitution on the fly? It's actually kind of nice that 1/2 is up on top, isn't it? You like that? So who has it? Tan inverse of something. Is it just tan inverse of x over 2? Take the derivative of that and check. Tan inverse of x over 2 should be 1 over x over 2 squared plus 1. 0.8 times 1/2, right? So I think we did it, yeah? Just do a little u substitution on the fly. And then, okay, now we can return to the conversation of today, and that's actually to like plug these in and take the limit. So what do we have? Tan inverse of 1 minus tan inverse of b. And actually, maybe we can just write down the answer now. What is tan inverse of 1? That's pi over 4. that's not really involved in the limit, is it? I mean, really the only thing I'm caring about is this. What's the inverse tangent of negative infinity? What does inverse tangent approach as we approach negative infinity? You have the graph in your mind? Pi over 2? Yeah, negative pi over 2, right. So is it okay to say negative, minus negative pi over 2 there? This requires like a little knowledge of trig to know that. And then so what do we get? 3 pi over 4? Yeah. Cool. So again, I guess we should also have said instructions on all of these will also sound like this. Everything is not always going to be all peachy like this. Sometimes the answer will be like, when we get to this last stage, we'll take the limit here, and it won't be a number, right? It'll diverge. In which case we can say that also then does the job of what it says here. Did you just show that the integral diverges? Yeah, that's what you just did. Are we still tracking with the examples on there? We skipped one? For later then, you know? All right, well this one's...
How does that one prove that it diverges?
It doesn't. It converges to 3 pi over 4. It said evaluate the integral. Or, in the process, you'll also have showed that it diverges. If it diverges. Yeah, so do one of the two. It either evaluates to some finite number, or it diverges. And that work would imply the same thing. So what do we do here? Uh-oh. We have two infinities involved. What are we going to do?
Break it up.
The integral from negative a to a, and then have a approach infinity.
But you could just go from negative infinity to
Yeah,
0 to
yeah, I guess, so this brings up a very, very, I'm just going to tell you that we're going to split it up the way Maddie said. But you do bring up a very interesting idea, and this is like the idea of uniform convergence yeah, I don't know how much I want to talk about it, but, because it's not like that important to this course. But you're also making a stronger demand. This is we don't really talk about this. We don't usually talk about when we evaluate a limit, that like, we think that it shouldn't matter what the answer to the limit is, depending on the speed you approach the thing. But what you're also demanding beyond what we're going to demand is like that they approach at the same rate. Because like we say, you want limit of both. You want to approach infinity and negative infinity like at the same time, kind of. So we are going to break it up into two integrals. That is from negative infinity to a number of your choice, like maybe 0 something, and then from 0 to infinity. And then we'll have just two problems of the type we've already solved, right? But maybe we choose two different letters or something. How about a? The limit as a goes to negative infinity, a to 0 of this thing. So that's half of the integral, if it even converges. And then the limit as b goes to positive infinity, 0 to b of the same thing. And the thing we want to be careful of is if either one or both of these two integrals diverge, then the whole integral will diverge, okay? Now I think in this case we're pretty safe, but I just wanted to give you that warning. We've done this one already before today, so let's just write it out again. Tan inverse of x on the interval at 0 to, I don't know, I'll just do it that way, yeah, plus tan inverse of x on the interval 0 to b. With some limits. Oops, I forgot the limits. All right, so someone will have to tell us what the limit, what the inverse tangent of 0 is. Yeah, 0. That was a good choice to put 0 as the middle here. Though it doesn't really matter because whatever it is, it looks like we're canceling it out over there, right? So, whatever. But if we take the limit, as a goes to negative infinity, this thing is just not even part of that question, right? That doesn't ever change as a changes. But this we need to answer. We already did today. What is that? guy? Negative pi over 2, right? As we go to negative infinity. So that'll be a pi over 2. And symmetry almost demands, doesn't it, that this also be pi over 2. Is the limit as b goes to infinity also of tan inverse of b also pi over 2. So this is cool. What do we get? That's good. We should have waited for Tuesday for this one. That's good. The area under this function. This is like tremendous. At every moment we need to in this course like stop by and step back and like appreciate like, oh, we just calculated like the volume of something crazy, you know. Or here, like we just integrated from negative to positive infinity under this function. We got like an answer like pi. Like what? Why should we? And why, for the pre-calculus student, why should this function, this rational function, have anything to do with pi? Right? Let that bake your noodle. Okay. Think about that all day long. You won't be able to sleep tonight. Why is there a pi even involved in that? 1 over x squared plus 1. The area under that is pi. Let's do another one. See how we're doing here. Whew, we gotta keep moving. So let's carry on. This is nice one that we know how to integrate that thing. It's great. So we'll do that. We're getting good at this now. What's your favorite letter now? What would you like? Q. Okay. You can choose your own letter on your own notes. Okay. From 1 to Q, 1 over x dx. My pen is killing me, man. Have you noticed that it's not really working for me? What's the antiderivative of 1 over x? Oh yeah, that's right. No. Oh man, this is no good. Sorry. Let me see if I have another pen that would work better. I don't know. I got a few. And this doesn't work at all. Okay. It's probably because I throw it around. Nope. It's not even touching the board. Why is it right? Okay. I don't know what to say. Okay. What does that say, though? Let's interpret. I'll just try to be careful. ln cubed, good job. ln cubed minus ln1. ln1, I know from calculus. That's 0. Okay. What's ln q as q approaches infinity? ln of infinity, I guess. What's that? So I think we just did this. And this goes back to the question I asked earlier. Is there any intuition we had about this? Because at first, 1 over x, I mean, that's also going down, isn't it? Like, this seems on the face when we start this problem from 1 to infinity. Like, that should be, like, how... What's going on? Like, shouldn't that converge too? Like, it's also... And apparently it doesn't, because we just didn't do anything wrong now, right? And yet we got a divergent integral. Let's do another one. Type 2, we're calling this. Is this on there? Are we getting the right examples? Yeah. Okay. Good. What is improper about this? This looks so great. I love this. I love this problem.
It doesn't exist in there.
Oh, wait. Yeah, so we need to be on the lookout for this kind of problem too, because it looks innocuous at first, but it's actually an improper integral, isn't it? Because of the vertical asymptote, type 2. This is kind of a giveaway to put the title up here. Okay, but that's exactly what's happening. Integrands with vertical asymptotes at the limit of integration. I guess, is that what's happening here? Where's the vertical asymptote for this graph?
Gotcha.
Where's the vertical asymptote for this graph?
Oh no, this is something else.
He's also on the video. That's good. So how are we going to handle that? I guess that's the problem, right? Like this is the issue down here. If you're like trying to identify, it's not obvious if you just like glance at this, but 0 is the issue, isn't it? So I think we have a strategy though to handle this. What are we going to do?
Make it a letter.
Make it a letter, exactly. Like we can't integrate at 0, but we can integrate anywhere close to you. Like you want to take the integral from 0.0001 to 1? Go ahead. That's no problem for a first semester U. But like, so that's fine, right? So what's your favorite letter today? K. Okay. The limit as k goes to 0 this time, and maybe we even want to be more specific from the right, I guess, if we want to be really clear here. So from from k to 1 of 1 over root x dx. So let's see here, that's x to the negative a half. So it'll be x to the 1/2.
Okay.
Yeah, check that on it. Does that work for us? On the interval k to 1. So we get 2. We'll plug them in now. So 2 minus k to 2 minus 2k to the root k. How about? Is that cool? Yeah. Take the limit. What do we get? As k goes to 0, this time we're keep in mind what the limit we're getting here is. We get 2.
You started.
All good. It's like scared. Do you have any questions about that? Vertical asymptote at the limit of integration. What about type 3? Again, the title gives it away, unfortunately. But what's going on here? Where's the vertical asymptote of that rational function? It's not really a rational function, but whatever. It has a vertical asymptote at 1. Yeah, at x equals 1, and so then, yeah, this maybe isn't type 3, it's just type 2, like with a little extra piece here, right?
2.5.
So, yeah, if we know how, we're lazy mathematicians, so if we already know how to deal with limits of integration, at the limit there's a vertical asymptote, then splitting this will like reduce this to 2 of the previous kind of problem, right? And we can add, integrals add, so we're good. So that's what we'll do. We'll like split this into the integral from 0 to 1 of this thing, which takes you determining what the vertical asymptote is, again. And it won't always be obvious, but here it is. Might have to do some factoring first or something. Good, so then each of those is a problem of the type we just did. 1 is the issue, right? So let's do, how about A and B again? Can I insert a limit here? As A goes to 1 from the left, and a limit as B goes to 1 from the right in front of those things. I don't know, haven't thought about it yet. It'll be like x minus 1 to the, it's to the negative 2/3, right? So that'll be like to the 1/3. And a 3 here. Check me on that. 1/3. I think that works. From 0 to A. Plus, same thing over here. Whatever I said here. 3. Again, if either one of these two integrals diverges, the whole thing is done. We're done. Okay, the rest is just limit work. Minus, plug in 0 for me. Is that plus 3 then? Again, it doesn't actually, well, it does matter a little bit. So what is that? 3, just 3, right? Minus 3 times b minus 1 to the 1/3. Okay, and then take limits. What do you get? 1 from the...
What is it? That is 3 on the right.
Did I say that
It's
wrong?
supposed to be up
I think it's 3 times.
Oh, I'm sorry. 3 times the cube root of 2. So what happens there and there? As we go from 1 from the left.
Then that's going to come out to 3. I got 3 plus 3.
Yeah, I think it'll end up being 3 plus 3 cube root of 2. But you're good. How'd we do? We only had 1 more? That's not too bad. You'll do great.
Sean Bates, please report to the main office. Sean Bates, please report to the main office.